Yeah, so electric fields we've already kind of talked about, but here we're going to give you this. I want to call that epsilon, the letter here, but I'm not exactly sure. The electric field. So I guess I'll just say E though for this here for simplicity, and just so my case my oh shoot sorry. So the electric field, which I'll say E, at any point in space around an electric charge is the force that would be experienced by a 1 coulomb, positive 1 coulomb charge at that distance r from the point. So this is a really similar property to when we were looking at gravity, right? This is like the equivalent of G, right? Particularly if you thought of G, right, as newtons per kilogram, right? So you're saying what would be the force that would be experienced, and it's a vector, you can have a direction, by a 1 kilogram mass. So just basically you cancel out the mass in that equation. And that's kind of similar to what we do here is we say, okay, well, what would be the force experienced by a 1 coulomb charge, right? So that allows you to sort of divide out that second Q in this equation. And so that also gives you a way to sort of talk about the field if you have a charge like this one down here, which is kind of Q1, and you pick a point in space, sort of like this point here. Now, there is no actual charge there, but we can still talk about what the electric field strength is here by considering, well, what would be the force on a 1 coulomb charge, or test charge, sometimes people say. Okay. Again, the principle of superposition applies here. If there are multiple charges around a point in space, then the electric field is just the superposition or the sum of all of those electric fields. So you just figure what the electric field is because of each individual charge, and then you can add those vectors together. So let's try it. Determine the electric field at the point P, which is 2 meters east of Q1 and 2 meters north of Q2. Now, because we're dealing with electric charge and not just with gravity or something, we have to recognize, we can have positives and negatives. So very important that this down here is positive and this here is negative, right? So that tells us we're considering what would be the force experienced by a positive 1 charge. So if we look at the electric field, this is 1 here, so it would be attracted to that one. And so we can kind of represent that as E1, or this would be the electric field at that point in space because of charge 1. And then if we consider what would be the case here because of Q2, well, Q2 is positive, so it would repel, right? So I would expect it. And it's stronger, right? It's 4 times 10 to the negative 5. And this one here is, I think that's a negative 6. Sorry if that didn't come out, but that here is 2 times 10 to the negative 6, which is definitely smaller. So that means this one here would be greater. So when we add these together, we should get something that would look like I'll just say that would be the total electric field at that point in space. Right. So we can figure out each of these individually. E of 1 would be because of charge 1, so we get Coulomb's constant, which we're probably just starting to memorize, 8.99 times 10 to the 9, times by the charge. It would be a negative here, but I'll just, put in the number because we know what direction it's actually going to go. And that's 2 times 10 to the negative 6. Divided by r, which is just 2 meters. Guess I didn't need that much. I think I did that already. 4495. And know the units here, right? It's newtons per coulomb. So this is the force that would be experienced, right, for each coulomb or whatever. And then we can do the same thing, effectively figure out the magnitude of E2, which is going to be very similar. Coulomb's constant stays the same, hence constant. Sorry, I can't resist the silly jokes. In this case, it's 4 times. Is that? I think that's actually supposed to be a 6 as well. Or at least I thought it was before when I calculated it, so I'll go with that. Which gives me 8990. And with those both being 10 to the negative 6, I expectedly this is just double the E1. And that means I can now figure out the total, which I already drew there in purple, so I'll go with that. That means the magnitude of the total electric field is plus the other one squared. Uh, 10,051. And I can figure out an angle. Let's go with this angle right here. And I'll kind of go in that direction. And that means if I'm doing the tangent of theta, it's going to be E2, because that's sort of represented with this side over here, which is the 8990 divided by 4, 5, which tells me that theta, just using a calculator for that, is 63.4 degrees. And yep, that makes sense because the opposite side would be longer. Therefore, E total newtons per coulomb. And because we were actually told these in terms of north, south, east, and west, I was going from west toward north, the way I kind of draw that arrow there. So I would say that's west 63.4 degrees north. That is oh, sorry, I just see a comment there. Why isn't the 2 scale? It is, and it was when I calculated it. Just looking back at I just forgot to write the. Thank you for that. Just a silly, maybe one of the downsides to calculating some of these ahead of time. I sometimes miss little things. But yes, we're dealing with forces. We'll deal with energy later, in which case it's not squared. So it's probably pretty important to not miss that it's actually going to be 4 in both of these denominators, which again you can double check my math on these, but yeah, sorry, I sometimes don't see the chat or miss these silly things. Sorry. I do see that question here in the chat as well about why they're positive. They technically you could say E1 would be negative, and remember, negative means attractive, just like with force, right? With electric force, if you get a negative value, it means they're attractive. So technically, I could put for E1, I could put that in as a negative and then interpret that as they're attractive. I took a little bit of liberties with this one in putting both the numbers in as positive because I already kind of knew, I had already figured out the direction. So then I was really just sort of dealing with the magnitudes of the numbers, right? Because I had already figured out that at that point in space, the electric field, because of Q1, right, would be attractive here, and so I'd already put in that arrow in that direction. And for E2, I figured out it would be repulsive because it's a positive charge down at the bottom here. And so I'd already put that whole like geometry together and figured all that out. So I just used the positive numbers because I at that point was like, well, I just want the value. But absolutely, you probably would be a little more thorough and a little more accurate if you actually put in the value in E1. If you wrote this in here as a negative, that probably would be more accurate. You get a negative value and you interpret it, or you use that as a check. Like I said, I maybe got a little carried away with just only figuring out the numbers. The other thing we want to do, which also sort of builds off this, but the +1 isn't, I don't think, is as significant here. Electric field lines, and you've seen them before. If you probably even done some stuff where you take a magnet and hopefully you put some paper over top of it before you put the iron filings on it or whatnot, and it sort of gives you a way to see some of the electric field lines. But we do have a definition for that, for how to actually draw electric field lines, and well, it's right there. They represent how a +1, so 1 Coulomb test charge, would move at any point in space. And so what's neat when you connect the lines is, if you looked at this one here, let's say, right, and you could say, well, what about this point right here, right? How would a +1 charge move if it was at that point in space? And you say, well, it would definitely move away from the positive charge, but it would maybe be slightly attracted to the negative charge. So you kind of expect, right, it would move like that. And so then it moves a little bit farther, and let's say it then gets to this point, right? Because at every point, the charge moves, but now, like, you'd sort of have to recalculate the new force on it, if you will, right? And so you say, oh, well, now it would still be repelled by the positive charge, but it's farther away from that, and so comparatively, right now it would kind of move like that. So you're kind of looking at, like, it would basically move in the exact direction of the line at that point. And further, if you actually looked at over time what would happen if you had a +1 charge, and you could say, well, it would actually follow that line, right? It would actually follow this line. And so you just look at the direction of the arrow, and you can start at the base of the arrow and just say, yeah, that's the path I would expect a +1 charge to take. A hypothetical +1 charge. We don't actually have one. And the other thing, I guess the reason I try to remember there's no charge there is because a +1 charge would also affect the other charges there, right? So that's why I sometimes feel it's important to remember there isn't an actual charge there, but if there were, that's how it would move at that point in space, right? So it doesn't actually affect anything else, right? And it's, kind of neat to maybe look at some of these points or some of these lines and convince yourself that, oh yeah, if there was a charge like right here, it would basically move at this point kind of pretty much straight toward the negative one. Yeah, it would be repelled a little bit by the positive charge, so it wouldn't be a perfectly straight path. But for the most part, right, it's getting, and the closer it gets, the more it is just like radially, like directly inward toward the negative charge. If you get something like parallel plates, which we'll deal with, it's a little bit of a simplified version. Probably there would be, a little bit along the outside like that, but usually we kind of ignore that part of it, or it's not really a big thing to consider. And here's, like, if you had a charge and a 1 plate, right, you can see again that's kind of any of these lines sort of represent the path you would expect a positive charge to take. So here is an example. Describe the path of an electron as it tries to move through a parallel plate capacitor. Right? So the particle's shown, the electron, and its initial, which actually I should maybe, well, you could call it V1 if you wanted to, but so we want to look at what happens. So we'll let it sort of get to this point here. We'll let it sort of get inside the plates. And then, well, what's going to happen once it's here, right? Well, it's repelled by the like charges, the negatives, and it's attracted to the positive charges here. So we'll assume that it's got enough velocity that it's going to make it through these parallel plates. But basically, yeah, because it's attracted, I would expect to see kind of a curved path. And once it's out, right, I would expect, I'll call this V2 equals constant, right? Just there's, sort of Newton's first/second law there, right? There's no force on it after it exits this thing, so its velocity would again be constant once it's outside of this field. But while it's in this field, right, it's going to accelerate because it's in this field. So we're not going to see linear motion in that sense, right? We're going to see, just like when an object's falling, right, it's going to accelerate, it's going to keep, picking up its speed. Also, the magnitude of V2 would be greater because this, while it's in here, right, it's accelerated in a different direction. So when it comes out, it's going to have, presumably, like the x component, if you will, of its velocity should remain unchanged, right? So if I look just at that component of its velocity, it should be identical to this, right? Because nothing's affected it in that direction. But we've added some, let's call it upward velocity, the way this is drawn, right? So we've added that component to it. So we've actually been able to increase the magnitude of the velocity, but we've changed the direction. I feel like wording it like that is sort of gives you the general gist of what's going to happen here. It's going to accelerate while it's inside there. Once it's outside, assuming there's no other charges anywhere around, it'll move with a constant velocity. Sorry, small correction there. Yeah, positively charged plate at the top, which these I think I mainly just took pictures from like textbook and whatnot. Just as sort of some definitions or things you might come across. So a dipole is just a pair of equal and opposite charges. So you could write that as plus Q, negative Q. And you can see the electric field lines are drawn. And from what we said before, this should sort of make sense, right? That because the electric field lines just represent what a positive charge would do. So of course here they would try to get away, and here they would try to, right, they'd be attracted. So that's what that would look like if you come across that term dipole. But also like worth thinking about and worth sort of considering some other arrangements you might have where if you had a pair of similar charges, what that might look like. And it would look almost exactly the same if these two were negative charges. It's just the arrows would all point in the opposite direction, right? Because the positive charge would want to go toward it. But yeah, you can kind of see, worth kind of doing on your own a little bit too, like just make two positive little points on a piece of paper and see if you can draw it, and then look back to something like this and check that it's virtually the same. This one I thought was kind of cool. You can look at, what would it be if I had negative Q and positive 2Q, right? What would that look like? And it's like, well, I know everything would go toward the negative charge, but the plus 2 is stronger, right? So it's going to compare how this would look like when it's just positive and negative, right? This up here, right? Compare the difference here and see if you can convince yourself of why you see the differences that you do when it's plus 2 and still just negative 1. That's really worth noting about this is, there's more lines at the 2Q, and that's kind of one of the ways we also sort of try to represent the strength is by the number of lines. So that's kind of the first little catch if you were going to draw this. So you got to say, well, I've got to have more lines if it's plus 2, stronger, and then I've got to have some of them, like I said, going towards the negative Q.